Life doesn't exist anywhere else in the universe that we know of. The basic building blocks of life are found just about everywhere we look, from asteroids and comets to interstellar clouds that stars and planets form from. The universe is fine-tuned for life, but it seems to be everywhere hostile to it, except for Earth. But is this really true? The lack of other confirmed life, either single-celled or intelligent, makes it seem so. Since Earth is the only life-bearing body that we know of, what makes it unique? What are the protections it offers against this hostility towards life? Are those conditions found elsewhere in our solar system? Next, we'll look at some of the life-friendly conditions on Earth and look for other places in our solar system to see if we can find similar conditions. Stay tuned. Earth is uniquely suited for life for a number of reasons. First, we should recognize that space itself is filled with life-hostile radiation. Radiation coming from the sun as well as intergalactic space. Cosmic rays, like all ionizing radiation, are damaging to DNA. Fortunately, Earth has a magnetic field that deflects most cosmic rays. In addition, Earth has an atmosphere that also provides protection. The atmosphere blocks 99.9% of the space radiation that impinges on it. Very little harmful radiation makes it to the ground. The atmosphere also blocks high-energy, low-wavelength radiation coming from the sun. The sun's atmosphere is completely opaque to the harmful radiation from space. The gamma and X-ray radiation coming from the sun, like cosmic rays, are also very damaging to living tissue, and high doses can result in cell damage and cancer. Without a magnetic field and an atmosphere, living tissue would be at great risk. Every solar system body has an atmosphere, right? No. For a body to have an atmosphere, it must have enough mass to gravitationally hold the molecules making up the atmosphere. This means there must be a right balance between mass and temperature of the body. The temperature is affected by the distance of the body from its parent star. More on this in a bit. It must also have the right life-sustaining components in its atmosphere. Hydrogen and helium are too light for retention of all but the largest and coldest of planets. Oxygen, nitrogen, carbon dioxide, methane, and ammonia are all common atmospheric constituents. All are heavy elements, but not all are hospitable for life. Other things can affect whether a planet has an atmosphere as well. Ultraviolet light can break apart molecules. Ozone is one example. Ozone is a heavy molecule that, when struck by ultraviolet light, dissociates into O2 and O. The two lighter components, then, can more readily escape. Cold temperatures can cause components, like water, to freeze from a gas into a solid, thus removing it from the atmosphere. Additionally, cratering events creates heat and can also accelerate loss. Atmospheres, therefore, are a balance of conditions both of the object as well as the object's position in the solar system. In addition to the temperature for an atmosphere, life is also thought to require the presence of water. Both are strongly influenced by the object's distance from the sun. It is a balancing act between too close, or too hot, and too distant, and too cold. Too hot means liquid water becomes vapor. Too cold and liquid water becomes ice. In other words, the Goldilocks zone is this just right distance from the sun where liquid water can exist. This narrow corridor is referred to more commonly as the habitable zone. More on this topic in another section. Another reality is that life likes long-term stability. The first life on Earth appeared, it is thought, about 300 million years after the formation of the planet. Intelligent life took more than 4.5 billion years, based on today's understanding. Fortunately, Earth's orbit is very circular. This allows Earth to stay at a consistent distance from the Sun, always staying in the habitable zone. A very elliptical orbit would bring Earth in and out of the habitable zone and likely result in large climate swings. Our orbital distance and circularity is very favorable for life. Furthermore, Earth has a large stabilizing moon. The moon helps regulate the Earth's climate by keeping it a nearly constant obliquity. The 23.5 degree tilt gives us the seasons. A constant obliquity ensures the seasons are repetitive and mild, at least for middle latitudes, that is. As an example, Mars' obliquity is currently an Earth-like 25 degrees. However, it varies from 0 to 60 degrees on timescales of thousands to millions of years. This is much faster than life can adapt. As a result, its seasons vary wildly as the obliquity shifts. Large seasonal variations are the norm without a stabilizing moon. Stability also comes as a result of external events, such as impact from asteroids and comets. Jupiter can be thought of as a protector of Earth. Jupiter's large mass has helped clear the solar system of debris that would otherwise threaten the Earth. Jupiter's effect can be observed by the absence of asteroids in the asteroid belt. At semi-major axes of major resonance, that is, the ratios of Jupiter's orbital period to the asteroid's orbital period, we can see a distinct region devoid of material. This material was either sent inward or outward of the solar system, early in solar system's formation. These regions of absence are known as the Kirkwood gaps. This creates a good news, bad news for our solar system. The bad news is that the inner solar system experiences periods of heavy bombardment, as observed by the crater records. That impact events can wipe out life and cause catastrophic short-term climate change. The good news is the bombardment set the stage for future life by bringing water to Earth. Other good news is that it happened before complex life, so the effect on existing life was minimal. This begs the questions: can we find Earth-like conditions elsewhere in the solar system? Or is there another set of conditions that can provide the same protection from the hazards of space? Let's turn to Mercury and the Moon. Both are very similar to each other. Neither, as it turns out, has an atmosphere, and neither have a magnetic field. Without an atmosphere, both experience extreme temperature differences between the daytime and nighttime sides. Mercury, being closer to the Sun and having a slow rotation, experiences an almost 1100 degree Fahrenheit variation between day and night temperatures. This would seem to create a huge problem for life to adapt to the extremes in both radiation and temperature. Venus is Earth's evil twin. It has almost the same size and mass as Earth. We'd expect similar conditions on both planets. Our expectations are wrong. Its atmosphere is extensive, but more isn't better. Venus has 90 times the atmospheric pressure of Earth's. It consists mostly of carbon dioxide, but it also contains sulfur dioxide, which is bad for humans and plants. Venus's surface contains almost no water and no oxygen. Oh, and its temperature is almost 900 degrees Fahrenheit, hot enough to melt lead. As if that weren't enough, Venus has no magnetic field and, of course, no surface water. While radiation isn't a problem, the excessive temperatures and pressures, coupled with the absence of water, makes Venus a very life-hostile place. Mars seems to be the best option. It has visible weather patterns and changing polar ice caps. It has similar obliquity as Earth, so that its seasons are very similar to that of Earth. However, Mars' atmosphere is less than 1% of the Earth's at sea level. Additionally, Mars has no global magnetic field. Mars therefore provides some, but not enough cosmic ray protection. Life would find it very tough going in modern-day Mars. Currently, no bodies of liquid water exist on the surface. The pressure on Mars is low enough that water ice would melt directly from solid to gas. However, subsurface water, liquid water, may exist. With the extra protection soil provides for cosmic rays and ultraviolet, microbial life may today be possible. However appealing, the life would have to survive large temperature fluctuations, experiencing well below 0 degrees Fahrenheit at night, even in the summer. But remember, the obliquity change will make today's temperatures seem mild in comparison. The Jovian planets aren't any more promising. They do have thick protective atmospheres and strong magnetic fields. They also have water in their atmosphere. However, there is no solid surface for life to develop or to exist. Any life would likely have to live in the clouds. Jovian moons seem to have nothing going for them. They're small, distant, very cold, too small for atmospheres and too small for internal magnetic fields. Many of them are covered with miles-thick layers of ice. One big drawback to the moons of the outer solar system generally is that there is no permanent atmosphere of any moon except Saturn's moon Titan. This has implications when it comes to cosmic ray and UV X-ray protection. Without an atmosphere and with large distances from the sun, these places are very cold. Jovian moons provide some tantalizing possibilities, however. Studies have produced photos of plumes of water on the moons of Jupiter and Saturn, including moons with thick surface ice. Jupiter's inner moon Io has no ice, but it is the most volcanically active place in the solar system. Not good for life prospects, having large amounts of solid surface buried underneath fresh lava. We know from our daily experience that ice floats on water. Could there be a subsurface ocean that the ice is floating on? Ice would provide the same protection from the space environment as an atmosphere would. Spacecraft flybys have revealed some surprises. Magnetic fields have been detected on many of the Jovian moons. The usual way of generating magnetic field in planets doesn't apply here, but other mechanisms could. We need another source. Salt water, a very good conductor. With the presence of Jupiter and dramatic evidence of tidal stresses causing volcanism on Io, we have our heat source. To confirm, we also see cracks in the ice on Europa, filling in with the warmer liquid water from below, shown in the image as dark streaks. We also see compelling pictures that seem to indicate structures that have moved and no longer appear to fit together, all possibly driven by subsurface water. Arthur C. Clarke uses this potential for habitability as a protagonist in his book series 2001: A Space Odyssey. At the end of the movie, 2010, the year we make contact, the spacecraft gets the following message from an intelligence that's living beneath the ice on Europa. So it seems the best possibility for life in our solar system, outside of Earth, may be the place we least expected.